Hello, guys. Welcome back to Chemistry with Miss Hernandez. Good morning, good evening, good afternoon, whenever it is you're watching. Thank you for tuning in. Today's topic is 6.18 electron shielding. 6.18 electron shielding. In your packet, if you have your packet, we're on page 28 to 31. If you don't have the packet, you can click on this link and it gives it to you. Make sure you're answering your review questions here and submitting on Friday, okay? You're submitting on October the 30th, this Friday, okay? And you can submit every single day as you do it, or you can submit them all on Friday. Okay, let's get started. I am working with fifth period again. Like I said, they're a really good bunch, and some of you guys would be lucky to be in this period, okay? So if you are, you should probably join us live. So the introduction talks about the goal. What is the goal of a roller derby game? Okay. Anybody ever watch or follow roller derby? I know there's movies about roller derby, and of course there's actual competitions about roller derby. Um, hey America, I'm glad you're here today. But today we're going to talk about roller derby because of the topic, okay? Roller derby and today's topic are similar in a way, okay? You have your picture here. It's basically roller derby is like going in a big old oval, right? Kind of like a street race, or like a NASCAR race, right? When you have a track and you're going around and around. Well, let's learn about roller derby for our introduction. Who's going to read? Irvin, Oscar, Yalexia, America, Arlette, Mario, Gabby, Efrain. Who's going to read?
I'll read.
Thank you. Thank you.
Roller derby is a popular sport, although it is unfamiliar to many people. The basic purpose is to set one team member, the jammer, past the opposing team to score points. Other members of the team serve as blockers to prevent the opposing team from stopping the jammer. Blockers interfere with the interaction between the jammer and the opponent by getting between the jammer and the skaters trying to stop her.
All right. And has anybody here know roller derby? Anybody here know actual roller derby? Okay, because no, you don't know it. Okay, I'm just asking. So what I've understood from roller derby, it's like a race, right? And the fastest person on your team is the jammer. Why? Because you want that jammer to pass every single person on that team, because the more times that they pass and go around that team, the more points they score for their team. But the jammer can't do it all by himself, right? He needs the help of blockers, right? Blockers are teammates that block the other team from basically they're to slow them down, right? The blockers will slow the other team down so the jammer can pass them and start to score points, right? And this person has to be really fit, really fast, and they're going to keep going around and around until they're able to get around as much as possible. And I don't know if you've ever seen where they kind of slingshot a person. You know, they're going in that curve. One person grabs them and they slingshot them around a certain amount of players. Okay. But the reason why it's coming up today is because yesterday we were talking about ionization energy. And ionization energy is the energy needed to remove electrons from an atom. And one of the ways is because of electron shielding. So that's how come we're talking about it today. Electron shielding. The attraction between an electron and the nucleus of an atom is not a simple issue. Only with hydrogen is there a one-to-one relationship that can be discussed in terms of direct charge. So hydrogen is the only element that's going to have one electron and one proton. And we know that electrons and protons, well, they have opposite charge. Protons are positive, electrons are negative. So there's going to be an electromagnetic pull between the nucleus and the electrons outside of the nucleus, okay? And for most cases, when it comes to ionization energy, as the size of the atom increases, the more protons and the more electrons you add, the number of protons and electrons will also increase. These changes influence how the nucleus attracts electrons. So let's talk about electron shielding. So we know that they are attracted to each other. Okay, yes, we do know that. Mostly because of that positive and negative charge. Now let's talk about in terms of trends, in general terms. Ionization energy of an atom will increase as we move from left to right on the periodic table. So this is our periodic table. As we start from lithium going to beryllium, going to boron, and so on, all the way to neon, the general trend is that ionization energy gets higher and higher and higher, right? Group 1 is lower than group 4 and group 2. So group 1 will be at the lowest, right? It'll be very easy to take away electrons. So beryllium will have a slightly higher ionization energy. And then group 13, 14, 15, 16, 17, and 18 will all supposedly increase, right? It's getting higher and higher and higher. You need more and more energy to pull those electrons off of that atom. At least that's what's supposed to happen, right? If you have your periodic table, on the side where you have a hydrogen, group 1 and group 2, ionization energy is really low. And as you go across, ionization energy will start to increase until you get to group 18, where it is the highest. It's really hard to lose electrons on this side of the periodic table. So it goes from being low to medium to high to higher, okay? And it's supposed to say high, but I guess I erased that when I was doing some writing. Okay, so it goes from being low to being high, okay, as you go across the periodic table. All right. There are several exceptions. There's going to be some exceptions to the trend, okay? There are several exceptions to the general increase in ionization energy across the period. One exception is between group 2 and group 13. Group 13 is over here. Boron, aluminum, and gallium has a lower ionization energy than group 2. Beryllium, magnesium, and calcium. That's not supposed to happen. This is supposed to be lower than group 13. That's not true. Group 13 will always be lower, and it's mostly because of electron shielding. Okay, and let's talk about that. The reason is because of a concept called electron shielding. Outer electrons are partially shielded or blocked from the force of the protons in the nucleus by inner electrons. And here you have a picture. I don't really like this picture. I'm going to draw my own. Okay, I like to see more color. I don't know about you guys, but I definitely like to see a lot more color when I'm talking about electron shielding. So here in the nucleus, you have a bunch of positive protons. Okay, so I'm just gonna go put a bunch of pluses. Then around that nucleus, you have orbitals. Okay, and orbitals have electrons floating around and doing their thing. Okay, then you have your outer electrons. So you have inner electrons and outer electrons, and you're going to see what I'm talking about right now. Okay, electron, electron, electron. So this is what it looks like. You have your nucleus with all those positive charges, right? All of those positive charges. You have inner electrons, right? These are your inner electrons. These are the electrons between the outside and the inside, okay? These are the electrons that are going to be doing all the work. These are the ones that are doing that blocking, that shielding of the nucleus. So they will block the power of the nucleus so that these electrons in the outer orbital, those valence electrons in that outer shell can easily come off or be removed. Okay? This is what we call electron shielding. Okay? Electron shielding. These electrons on the inside shield those electrons on the outside so that they can easily go away. Okay? That makes sense? Does that make sense, guys? All right. So that's one example of lower ionization energy as you go to the right. To explain how shielding works, consider lithium atom. Okay, so we're going to consider lithium. I'm going to take this off. I'm going to take this off. I'm going to redraw my nucleus so that it only has 3 protons. Okay. Okay, there you go. Here's an electron. Okay, there we go. So here you have, and you know what? Let me make them as dots so they can easily be seen. All right, here you have a lithium atom. Okay, lithium atoms have 3 protons and 3 electrons. The first orbital will have 2 electrons, and the outer valence electron orbital will have 1 valence electron. Okay, for a total of 3 electrons and 3 protons. Okay, now in the first principal energy level, you have 2. That's the one in black, right? This is your first energy level. And its valence electron is in the second energy level. That's the one that you see here in red. The valence electron is partially shielded from the attractive force of the nucleus by those 2 inner electrons. So here you have your nucleus. It's going to get blocked or shielded from these electrons. These electrons are going to do some blocking, right? They're going to block the power of that nucleus so that it's easier to get rid of this 1 electron. Okay? Inner electrons shield or cover up or block so that electrons can easily be removed. Okay? I hope that makes sense. Removing the valence electron becomes easier because of that shielding effect. I call it, blocking it or covering it up. There is also a shielding effect that occurs between sublevels within the same principal energy level. Specifically, an electron in the S sublevel is capable of shielding electrons in the P sublevel of the same principal energy level. This is because the spherical shape of the S orbital. The reverse is not true. Electrons in p orbitals do not shield electrons in s orbitals. All right, and there you have a picture of your s and your p orbital. But as usual, I don't like that picture, okay? If you have an s orbital, so you have your nucleus, right? And your nucleus has positive charges because of the protons, okay? So I'm just going to draw that. And I don't know what element this is, but you have an orbital that looks like a basketball, right? It's round all the way across. In the middle and of that basketball, on the inside is your nucleus. So imagine that this is your atom, right? This is your atom. This is the ball, the basketball around the nucleus. This is your nucleus in the middle. Now, it looks like a sphere. It looks like a ball, right? A basketball. Think of it as a basketball. And that basketball goes all the way around the nucleus. Okay? And then you have electrons in that orbital. So I'm going to put some dots, right? Just to represent. But you also have a p orbital. Now the p orbital, it kind of looks like a figure eight. Okay? Kind of looks like a figure eight. I don't know if you can see it there or if it's better like this. But either way, you have electrons in the s orbital and you have electrons in the p orbital. So this guy is going to be traveling in a sphere, right? It's going to be going around the basketball. It's going to go this way. It's going to go that way. It's going to go all ways. And then you have this p orbital. So this electron goes here, goes down here, goes down here, 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 and here. Now, this orbital, the s orbital, the one that looks like the basketball, will help shield this p orbital in case I need to remove this electron. Okay? But the p orbital, the one thing that they said is the p orbital does not shield the s orbital. Only the other way around. The only thing that's going to happen is that this guy, this sphere, will cover up and shield the p orbital so that we can get rid of it, right? But the opposite is not true. The p orbital will not protect or block for the s orbital. Okay? But it will block, the s orbital will block for the p orbital so that we can get rid of this electron. Okay? So this nucleus gets shielded by the s orbital, right? By the s orbital, so that I can easily take this guy off. And that's all it said in there, okay? Is everybody okay on that one? Do I need to repeat anything on that? Okay, I hope not. Let me know if I do, guys, okay? Because this is not an easy topic. All right, so now let's talk about an example. Let's go back to group 13 and group 2. So element aluminum. Element aluminum is group 13. Element magnesium is in group 2. Okay? Now, group 13 will always have 3 valence electrons. 2 in the s orbital and 1 in the p orbital. Okay? So, this s orbital will block the nucleus so that we can get rid of this electron. Okay? So ionization energy for group 13 is going to be lower. It's going to be easier to take away that electron, this electron, because of the shielding that the s orbital does. Okay? But if you're talking about group 2, group 2 doesn't have this p orbital. Okay? And I'm trying to erase it as best as I can without erasing the s orbital. This is what group 2 atoms look like. It's only the basketball around the nucleus, okay? So this is now magnesium with only 2 valence electrons, 1 and 2, okay? So these are the outer electrons. There's still some on the inside, okay? It says here, the electron being removed from magnesium is a 3s electron, which is only shielded by inner core electrons. Since there is a greater degree of electron shielding in the aluminum atom, it is easier to remove valence electrons, and its ionization energy is less than magnesium, despite the fact that the nucleus of the aluminum atom contains one more proton than the nucleus of magnesium. Okay, so here in magnesium, you have inner electrons that do shielding. Okay? These electrons on the inside will shield so that I can get rid of this one electron. But when it came to group 13, aluminum had extra shielding. Because remember, you got to think of, for aluminum, you have this electron right here. It's got extra shielding. It's got the inner electrons here. It's got the inner electrons, and it's got the s orbital protecting and blocking the nucleus. So it's easier to get rid of this electron than it would be for this magnesium because it's got extra shielding. Does that make sense? That s orbital, that basketball that's around the nucleus, is an extra shield of protection that magnesium doesn't have. Magnesium only has these inner electrons to do blocking. Aluminum has these inner, the s orbital as well, making this p electron go away a lot easier. Okay? I hope you can see that. Okay, I know it's not the best drawing. All right. There's one. Now, there's another exception. Group 15 and group 16. All right. So now we're talking about group 15, nitrogen and phosphorus, versus group 16, oxygen and sulfur. Now we know, supposedly, according to the trend, group 16 should have higher ionization energy than group 15. But that's not true. Group 16 has lower ionization energy, and we're going to talk about why. Okay? But I need to do some erasing. Atoms of group 16 have lower ionization energies than atoms of group 15. Hund's rule is behind the explanation. In a nitrogen atom, there are 3 electrons in the 2p sublevel. So let's talk in terms of, nitrogen and oxygen. Sorry, I was already writing. So we got nitrogen, group 15. We got oxygen, group 16. And check this out. So we have 2s, 2s, 2p, and 2p. Okay. Nitrogen will have 5 valence electrons. And these arrows that you see, they represent electrons. Okay? Here you go. Here's group 15, nitrogen, group 16, oxygen, and these are just the valence electrons, okay? These are the electrons available to be lost or gained. Okay, right now, all we're trying to do is we're trying to lose electrons, right? Ionization energy, removing electrons. Now, if you look here, according to Hund's rule, you are supposed to spread out electrons evenly and then double up. Well, we did that for nitrogen. I had 2. I have 3, a total of 5. Okay. For oxygen, I'm supposed to have 6. Here's 2. Here's 1, 2, 3 more. Here's the 4th one for a total of 6. Now, why does oxygen have low ionization energy? Okay. So this guy is going to have low ionization energy. That's okay. We're trying to figure out why. Okay. Now, electrons, they're both negatively charged. If I have 2 electrons that are negatively charged, they're not going to get attracted to each other. They're going to push away from each other, okay? So with that extra push and the shielding effect that all the other electrons do, this electron right here can easily be lost. Okay, and I'm just going to put here lost. Why? Because of the protection of the s orbital, and because this guy, this one right here, is pushing this electron out to be lost. Here, for group 15, is there a second electron here that can push this guy out so that it gets lost? No. Because this guy doesn't have the extra push that this guy provides, ionization energy is lower for group 16 than for group 15 because we don't have that extra push of that electron. Okay? And that's all it says here. Okay, and it makes it super confusing, okay, because they use a lot of terms that we haven't talked about yet. So in a nitrogen atom, there are 3 electrons in the 2p sublevel. Each is unpaired. Okay, so that sentence is talking about this one's right here, unpaired electrons. Okay, and then it talks about in oxygen, there are 4 electrons in the p sublevel. 1 orbital contains a pair of electrons. So now they're talking about this one right here. 4 electrons. Instead of having them all unpaired like you do here, there's 1 paired electron. Because of this electron pushing this guy out, ionization energy is lower for group 16 than it is for group 15. Okay, and that's all it says here. In an oxygen atom, there are 4 electrons. It is that second electron in that orbital that is removed in the ionization of oxygen atom. Since electrons repel each other, it is slightly easier to remove electrons from a paired set of oxygen atoms than it is to remove an unpaired electron from nitrogen. Okay? All it is that this electron right here pushes this guy out. This guy pushes this guy out, making low ionization energy for that group. That's it. Let's watch the video and we're done.
Okay, let's take a quick look at electron shielding. So what is electron shielding? It's when the outermost or valence electrons are shielded from the pole of the nucleus by the inner electrons. This results in a weaker electrostatic attraction between the nucleus and the valence electrons. The valence electrons need less energy to remove, which means the ionization energy decreases. Let's look at an example here. We have K, which is potassium. The electron arrangement is 2, 8, 8, 1. Okay. Now, this electron here, that's called a valence electron. It's the electron in the outermost shell or outermost energy level. The other electrons, the inner electrons here, they are called shielding electrons. Now, there's an electrostatic attraction between the positive nucleus here and the outermost electrons, okay? So the shielding electrons, they shield this valence electron from the full attraction of the nucleus, which means the valence electron is easier to remove. And potassium can lose the valence electron to form K+, which is a 1+ ion. Okay? So, the first point here, atoms with more filled energy levels have more shielding electrons. Therefore, the ionization energy decreases down a group. So if we look at an example here, these are ionization energies of group 1 elements, lithium, sodium, potassium, rubidium, and cesium. Now if we look at the ionization energy, we can see there's a decrease, okay, a downward trend. So that means as the atom gets bigger, as we're adding more filled energy levels down the group, the energy required to remove the electron, the ionization energy, that is decreasing. And one of the reasons for that decrease there is there are more shielding electrons which decreases the attraction between the nucleus and the outer valence electron. Okay?
All right, so that's just another video about shielding. All right, let's summarize today's topic. Electron shielding refers to the blocking of valence shell electron attraction by the nucleus due to the presence of inner shell electrons. Okay, so outer electrons get shielded by inner electrons. Electrons in an s orbital shield p electrons that are in the same energy level because of the spherical shape of the s orbital. The last point, electrons in paired spin configurations are slightly easier to remove than unpaired electrons. All right. Thank you guys for paying attention. Thank you, fifth period, for being so good.